All right, so good morning, everybody. Lecture 20. So today we're going to start on, and again, just want to check, am I audible?
Yes, sir.
Okay.
Yes, sir.
So today we're going to start on probably one of the most important and interesting topics of quantum mechanics, which is the addition of angular momentum. So this is one of the most fundamental questions in quantum mechanics. And the reasons for this is that almost anything that is of interest in quantum mechanics in the physical world tends to have some sort of angular momentum, right? So for instance, we know that electrons have a orbital angular momentum, right? Sorry, spin angular momentum. Well, they have both, right? So this is the spin angular momentum. Then when you have a, let's say, a proton and an electron in a bound state, this electron has a orbital angular momentum, which arises by virtue of its rotation around the nucleus. Of course, quantum mechanically, this picture of an electron moving in along a fixed trajectory is not correct. You have to speak in terms of wave functions and then a probability distribution for the electron, an electron cloud, right? But you know, this helps to illustrate the concept. So, so whenever we have a system like this, right? So here you have the electron. It has some orbital angular momentum. It can also have some spin angular momentum, right? Similarly, the nucleus can also have its own spin and orbital angular momentum, right? So whenever we talk about such a composite system, what we want to do, what we try to do in classical mechanics and quantum mechanics, right, is we try to define quantities which apply to the whole system, right? So for instance, we try to talk about the total momentum or the total energy or the number of particles or the total angular momentum. So the simplest example is that of linear momentum. So when you have linear momenta, when you have a system with n independent particles, then you say that okay, linear momentum is just the sum of the momentum of each of the individual particles, right? And now let's say that I ask you, somebody asks you to write down the wave function for these n particles, right? How will you do that? So, and you want to be able to act on that wave function, on that state, with this total momentum operator, right? So that that wave function which represents these n particles, this collection of particles, can be said to have a total moment and a linear momentum. Right? So how would one go about doing that? Right? One simple guess is that, well, we can start from the single particle picture, right? So let's say that I have the wave function of my ith particle, and it depends on the on some momentum vector, right? So, or I can write it like this. This is equal to, if I want to write it everything down in terms of the complete vector rather than the components. right? I would have something. So as I've explained many times before, this is the actual vector, these are the components, but we often refer to this itself as the vector in any representation. So if you want to define the state of the whole system, right, which has n particles, one way to do that, so this state would be a function of these n momenta. So one way to do that would be to just take the product of the individual states. Okay, and I should put an index on the psi also, because the form of the psi can also be for each part. Okay, so now you have this many particle Hilbert space, right? So you started with a single particle, right? Single particle with some Hilbert space H, right? And what is H, for instance, for a particle moving in 3 dimensions? H is a space of all possible states, right? So for what are the kinds of states? If you work in the position representation, you would write psi of R, right? As a single particle state, right? And what would be the requirement for psi of R? You would require that all of these states are square integrable, right? Is finite. So this implies that psi of R belongs to, we write it like this, L square, square integrable R3, meaning this the space of square integrable functions defined on R3, right, in 3 dimensions. Now, how would you write down what would be the Hilbert space of n particles? Well, let's start with 2 particles, right? Now, this is something that I went into in some detail in our first semester also. Okay. So for 2 particles, what would be the Hilbert space? Anybody?
Tensor product of
It will be the tensor product of these 2, right? For brevity, I'll just write this as x squared. And also, by the way, is this finite dimensional or infinite dimensional? This H. Anybody other than Sumuk? Huh? Sorry? Pooja? Is this state finite dimensional or infinite dimensional? This L square.
Infinite dimension.
Infinite dimensional, right? Why? Because I mean, you're talking about the space of continuous functions, and there are an infinity of functions. And so here we are not talking about the spin degree of freedom of the particle, right? So if you have the particle has a spin degree of freedom, then for instance, what would happen is you would have, so let me write that down also. Sorry, my handwriting is all over the place for some reason. With spin degree of freedom, your Hilbert space would be this H, which is your position space. I'll call it H of R to distinguish it from the spin Hilbert space. And H of S is the spin Hilbert space. Is this space finite dimensional or infinite dimensional? Ashutosh?
It's infinite
the Hilbert space of a particle with some spin.
I guess a finite.
Finite dimension. What is the dimensionality?
2.
With the, yeah, go ahead. Go ahead. Jita has started opening up, flipping through a book very quickly. Anybody else? What is the dimensionality of the Hilbert space? Abhishek? Varsha? So this is a spin J particle. The Hilbert space dimensionality is 2J plus 1, right? It's finite. And then when you take this tensor product, this will again be infinite. Okay. All right. Now, so let us go back to the case of a spinless particles, right? For right now, for our purposes, let's just talk about spinless particles. So that means they will have orbital angular momentum, but not spin angular momentum. Spinless particles. So what is the Hilbert space of n such particles? H of n is H of this R, and I'll just leave out the R index, okay, unless it's needed. R. N time, right? So this is, what is this called? This is called the tensor product. Now, how do, what is the form of states in the tensor product space, right? So again, this is something that I covered in some detail in the first semester. So I expect you all to, if you have forgotten, to please go back and jog your memories, read through the notes, okay? But I'll remind you just a little bit that let's say that you have a state psi1 which lives in one Hilbert space, okay? And so I'll put an index 1 to n to indicate that this is the state for the ith particle. So if you have a state psi1 in the first Hilbert space, right? And you have a state psi2 in the second Hilbert space, then how would you write the collective state? You would write it as psi1 tensor psi2, okay? And what would this look like in terms of components? So in terms of components, psi1 is what? It's psi of r, get r, d cubed r, right? Similarly, psi 2 is integral of and a 1 on the r's also, because the r coordinate is going to be different for the two states. Get of r2 d cubed r2, right? So what is the tensor product? The tensor product state can be written as the product of these two, right? Psi1 r1, psi2 r2, and then get r1, get r2, integral d r2, right? So this is the tensor product state. Again, if it helps, you can always think back to finite dimensional vectors, right? So if you have two vectors u and I, so let's say that for finite dimensional case, how would you write down a vector u? You would have the components of the vector, right, times some basis state, right? So for instance, your basis state, we'll write it as E of I hat. So for instance, E of I could be x, y, z hat, right? And similarly, V is equal to B of I hat, right? So then what is this U tensor V? U tensor V is Ui Vj EI, EJ, like this, right? Sum over I. So what is the base? What are the basis vectors of this tensor product space? The tensor product space has the basis. First of all, if the dimensionality of U is, so I'll put a prime over here because they can be different dimensionality. If the dimensionality of U is M and the dimensionality of V is N, then what is the dimensionality of U tensor V? Anybody? Ashutosh? Bhartin? Varsha?
M plus N minus 1.
M times N. M times. We are talking about the tensor product, okay? Not the direct product, direct sum. If it was the direct sum, then it will be M. So and now we can ask what happens to operators on these states. So for instance, let's say you have a state, you have a matrix A which acts on U, and you have some matrix B which acts on B, right? Then how would I write down something which acts on U and B? I would write that down as A tensor B. And how would this act on U and B? A would act on U and B would act on B, right? So in terms of components, what are the components of U tensor V? Ij is just Ui Vj, right? I goes from 1 to M, J goes from 1 to M. What are the components of A? The components of A are just the matrix elements Aij. Components of B is just a matrix elements. What are the components of A tensor B? Well, this will have 4 indices, right? So you'll get Aij, Bkl like this. How will this act on U and B? You'll get Aij, Bkl, U. Which index will I put here? J. And VL, right? So you will have a contraction between the J index and the L index, right? Okay, so now, I mean, I think that many of you are very fuzzy forgotten. So for today, I'm going to just move forward and give you some more definitions, and then hopefully you will go home and well, you are home. You will read up your notes from the first semester, and then in the next class, you can tell me what your situation is, right? Whether you, having read those notes, understand what I did here or not. So now we can come back to this picture, right? So this is just the infinite dimensional case. And for this, we can ask, for instance, so we have the momentum operator, right? Let's say P1. The momentum operator acts on this state psi r, right? And similarly, you have the momentum operator P2, which acts on the state psi 2r. Okay. So how will I write down the operator P? So for the classical case, right, when I'm just describing particles with classical momenta, this is how I write the total momentum, right? I just write it as a vector sum of these n objects, right? But in the quantum mechanical case, you have to be careful. The reason is that in the quantum case, your operator P, right, it acts on some Hilbert space. Which Hilbert space? Which Hilbert space does it act on? for n particles. Abhishek?
Could you repeat that, sir?
For n particles, I have an n particle Hilbert space. See, this is why I tell you guys to turn your videos on, because if you turn your videos on, you will have to maintain some sort of focus in your interactions with me. If you keep your videos turned off, then, well, your mind can drift, you can do whatever else. But distracted by it. So P acts on Hn. Which is H1, which acts on this 10 product tensor. So let me just pause the recording really quickly and ask you a question. Are you guys following any of this, or have you completely forgotten everything about tensor products? Just be honest with me so I can understand where you stand.
I understood so far. I mean, I don't have any confusion.
Okay. What about the rest of you? Can I just get some status updates?
While you're explaining, it's like coming back to me.
Okay. All right. So this is like that song, and it's all coming back to me, right? Okay. So P acts on this Hilbert space. So now we are in this situation that we have to write. We have these individual operators, where P1 acts on H1, P2 acts on H2, and so on. But the operator P, which should represent the total momentum, it acts on this tensor product space, right? But in some sense, this P, it should come from taking the classical P, right? You have the classical P. And when you quantize this classical P, you should get the quantum P. Right? So how do you write down an operator corresponding to, let's say, P1, which acts only on H1, but is actually an operator which acting on the n particle Hilbert space, right? So I'm going to write it down first. So I'm going to write it with a prime to distinguish it from this one, because this operator is a single particle Hilbert space operator. So P1 prime is P1 tensor identity, tensor identity, tensor. You follow? So when I act on this n particle state with P1 prime, what will it do? For all of the factors within this n particle Hilbert space, H2 to Hn, it will not do anything, right? Because there is just the identity of it. For the first Hilbert space, it will act on that with H1, with P1, right?
So it's equivalent to just acting on the first particle.
It is equivalent to that, but it is very important to remember that this operator and this operator are not the same. Okay, so for instance, again, working with finite dimensional Hilbert space, if I say that my dimensionality of my Hilbert spaces is something, let me call it Q, then dimensionality of Hn is q to the n. Okay. And what is the dimensionality of an operator which acts on a q-dimensional Hilbert space? It is q by q, right?
Yes, sir.
In terms of a matrix, it will be a q by q matrix. And what is the dimensionality of an operator which acts on the n particle Hilbert space?
Q power
It will be
n.
qn times qn, right? Right?
Yes, sir.
So you see, this is very different from this. For instance, if you say that q is equal to 2 in the simplest case, then the dimensionality of this single particle operator q square is 4. And let's say you're talking about 4 particles, then the dimensionality of your is how much? 2 to the 8 is 256.
256.
Right? So you see, this is a 4 by 4 matrix, and this is a 256 by 2. Right? Now again, some of you might question, how am I going shuttling between infinite dimensional and finite dimensional? Right? For instance, I said these are all infinite dimensional. Well, the thing is that, see, nothing in life is actually infinite. This is just a mathematical idealization. If you actually have to implement this, let's say numerically, what would you do? You would take your momenta and you would discretize, right? You would take your particles, put them on the real line and discretize the real. So you would reduce your infinite dimensional system to a finite dimensional system, right? So that's one reason why I don't have any issues going back and forth. Also because it is the only way that I can explain these concepts. If I said that these are infinite dimensional, then dimensionality of P1 would be infinity times infinity, and dimensionality of P1 prime would be infinity times infinity, and that would not make any sense, and the listener would not be able to understand what I'm talking about. Okay. All right. So similarly, yeah.
Sir, I have one doubt. Let us assume there is an interaction between particle 1 and 2. So my measurement of momentum of P1.
Okay. So all of those things will come later. All right. Okay. I'm just talking about the definition of operators. Is defining an operator in this way does not mean that I am restricting any interactions between particles. Okay. This is simply saying that this operator acts only on the first particle. That's it. Okay. Particles can be interacting or non-interacting. I've not said anything about that. So this Hilbert space, right? It contains all of the states. Okay, all possible n particles. Is that okay? I mean, unless your question is something.
Yes, sir. That's fine.
Okay. So now, similarly, we can define P of I, right? P of I will be 1, I minus 1, P of I, and prime here, identity, I plus 1, identity n. Right? So this is the identity operator everywhere except for on the ith state. Okay, so this is how we define operators which are the equivalent of these P1s of these classical momentum. right? Now that I have defined my operators, and these operators, they act on what? They act on Hn, right? So then I can define the total operator P. The total operator P will be what? It will just be the sum of all of these operators. And now you see this operator, each one of these operators acts on the Hn Hilbert space, right? H to the n Hilbert space. So if you take the linear sum of these, you will get another operator which acts on the H to the n Hilbert space, right? If you want to write this mathematically, you would write it like this. Hn to H. What this tells you is that P is something, the state, again, therefore, it's Hn. N and N is Hilbert space. Okay. So please don't get confused between these two notations. This is the tensor product of all of these Hilbert spaces. This is just a single particle. So this operator P, it acts on this tensor product space. And it gives you another vector in the tensor product. So this is how we would add linear momentum. Okay. So is this making sense? Well, we'll look at a few examples later in a second, and then hopefully it will make a little bit more sense. Okay, so spinless particles. Right. So we can look at an explicit example of this. Okay. So let's just take our particles to have really simple form, our states to be plane waves. So psi 1 r1, or I'll write psi k for the kth particle, is, I will just take it to be exponent of minus I pk dot rk, right, divided by h. So this is the simplest single particle for a free particle, right? For a in the continuum, right? So this is a free particle. And what is the momentum of this free particle? The momentum is just pk, right? Just these numbers. All right. So now, how do I write down the state for these n particles, all n of them particles? What is this R1 to Rn? Well, this will just become the product of all of these, like this, right? And putting this expression in here for each one of them, what will I get? I'll get exponential. And now all of the exponentials, you will just add them, right? The exponents will just add. So I can just put everything in the exponent like this, right? So here I'll get P1 dot R1, P2 dot R2 plus Pn dot. This is my n particle state, right? And all the particles, and it is very important to remember because it's easy to make this get confused between these two things, is that there is a very clear difference between having a superposition of a particle which is in two different states of momentum. Okay. You can have a single particle in a superposition, so that you would write the components of the state vector as, let's say, something like this: exponent minus I by h bar p1 dot r. Okay, and then you'll put some alpha over here and some beta and exponent minus I h bar p2 dot r. So what is this? This is in a superposition of states with momentum P1 and P2. Okay. So what is this? This is a single particle, but the momentum of this particle is not well defined because it's in a superposition of two different momentum eigenstates. On the other hand, if you have two particles in a tensor product space, right? So how do you write down the state of those two particles? You would write down, let's say, something like, sorry, psi of R1, R2. You would write it as psi 1, R1, and psi 2, R2, right? Now, where this psi 1, it can have momentum, let's say P1, and this can have momentum P. But that does not need to be the case. This could also be in a superposition of states like this, of different momentum eigenstates. This could also be in a superposition of momentum eigenstates, in a different superposition. So what is the difference between these two things? The difference is that when I measure the momentum of this particle, I get only one quantum number, only one momentum, which has three components. Right? But when I measure the momentum of this state, so even though I have two different momenta here, right? Two different numbers, you might think, well, I will get to no, right? Because you have one momentum operator which acts on this. On the other hand, the momentum operator acting on this will give you two sets of quantum numbers, one for the first particle and another for the second. Okay. Just to clarify. All right. So now, by the way, it is in the process of doing all of this that we also run into the concept of bosons and fermions. Okay. So which I haven't mentioned explicitly, but what happens is that you consider what happens to the state of an n particle system when you switch any two particles, and right. So one can ask what happens to this state if I exchange R1 and R2, and it turns out there are two possibilities. The state can either be the same or it can pick up a negative sign, right? This is when you're working with identical particles, right? So for instance, 1 and 2 are both electrons, right? So electrons are completely indistinguishable from each other. So if I exchange R1 and R2, the state will not change, right? But what do I mean by when I say the state will not change? What I actually mean is that the probabilities associated with the state will not, right? So you will get the condition that psi square is equal to 1, which means that psi can be the new psi after exchanging can be plus or minus of the original. For the positive case, you say that your particles are bosons. For the negative case, you say your particles are fermions. I will mention that in a later class in more detail. Okay. So for now, in case you have been thinking about it, I don't want you to worry about it too much, about the fact that I'm writing on these products, because if you have fermions, then you have to anti-symmetrize. You have to take the sum over all anti-symmetric permutations. And if you have bosons, then you have to take all the sum over all permutations. Okay. But here I'm not doing that. I'm forgetting about the fact that they are bosons and fermions. I'm not worried about that. My goal is just to explain this tensor product.
Sir, these are not operations, like bosons and fermions are particle names, right?
What do you mean by that?
No, sir, like when you said if they are bosons and if they are fermions, these are types of particles? Are they types of?
Yeah, they're types of particles. Right?
Okay.
They're particles with certain kinds of behavior under exchange.
Okay.
I will have a class devoted to that later. Okay? For now, let me come back to the addition of angular momentum. Okay. Can I take another 10 minutes, 10, 15 minutes? Is that okay? If it's not okay, you tell me, okay? So returning to angular momentum. All right, so now we look at what happens if we have a part system with two particles with some angular momentum, okay? With angular momentum. So now, how do I describe a single particle with angular momentum? So you remember I have these operators, Jx, Jy, Jz, and J square, right? And of these operators, I take these two to form my complete set of commuting operators, right? And then the eigenvalue of J square on an angular momentum eigenstate So this is my angular momentum state, eigenstate. What is the eigenvalue? J times j plus 1. Right? What is j? Where j is a half integer. You would write it like this. Okay. And what is the what is the eigenvalue of jz? Jz on this angular momentum eigenstate is some m where m takes what value? Minus j plus 1 till j minus 1 to j. Right? And how many such values are there? So if I say dimension, I get 2j plus 1. Right? So what this means is that my angular momentum eigenstate can be written in terms of these two eigenvalues. It can be labeled with j and with m. What is j? J is the total angular momentum. M is the z component of the angular momentum. Okay? All right. And again, the total angular momentum is not actually j. Like for instance, if you do a measurement, what you do is you measure the eigenvalue of j square. So if you wanted to assign a number to the total angular momentum, you would say that number is square root of j times j plus 1. But we just denote the state with the number j. Okay. All right. So now I have two particles. And before that, what is the dimensionality? So this lives in a Hilbert space. I'll call that h of j. And what is the dimension h of j? Varsha?
Yes, sir.
What is the dimensionality of this Hilbert space?
It's j. So I think it will be 2j plus 1.
2j plus 1. So now we have two particles with angular momentum. Okay, so how will I describe the states of these particles? The first particle will have some j and m, and the other particle has some j2 and m. Right? So this lives in the Hilbert space of the first particle, which is hj1. This lives in the Hilbert space of the second particle, which is hj2. Right? So these are my two particles. Now I want to write down, I want to say what is the total Hilbert space, right? So the total or the composite Hilbert space, right, for the composite system is, anybody? Answer is very simple. Please tell me quickly. What's up?
2j1 plus 1 into 2j2 plus
hj1, hj2 tensor. Is this what you were saying?
yes.
I actually said utsav. but Aditya answered anyway. That's fine. So the tensor product of Aj1 times 2, right? And what will be the state of the system? The state of the system can be written as J1, J2, M1, M2. I can also write it as J1, comma M1, J2, comma M2. Madam, one second. All right, just office work. So this is J1 M1 and J2 M2, right? So this is the tensor product. Okay, fine. But now we want to ask, for instance, what is the total angular momentum of these two of this system? Right? So now we know how to define operators which act on the composite Hilbert space, right? So we know how to define something like the total momentum operator, right? So as an example, I will ask, I want to define the momentum operator J of Z in terms of J1Z and J2Z. How will I write this down? What will be the expression? Oh, okay. Well, I guess maybe somebody might have issues with Zoom. So what will be the form of this expression? It's what is this Jz? It's the sum of the two Z components. As an operator, how will I write it? Very simple. I mean, we just did an example, right, for the case of linear momentum.
Jz1 plus I1 plus I1 plus.
So it will, sorry?
So it will be like sum of Jz1 and Jz2 in 2 dimensions.
Yeah, it will be the sum, but you have to be a little bit.
Yeah, so Jz1 cross I1, tensor product I1 plus I1
Jz1, tensor product what?
I1.
I2.
I2 and plus I1.
It's okay. Similarly, similar again. See, if I'm not careful.
ZZ
I1
cross 1 1.
Thanks. So I think as long as you're following along on YouTube. So this is the total Z component operator. Okay. As an exercise, it is useful to evaluate this for a spin 1/2 particle. Okay. For 2 spin 1/2 particles. Write down the form of Jz. Okay. So I'll leave it as an exercise for you all. And in our next class, I will ask you if any of you have managed to do it. And where you have to remember that the single particle these operators are just the polynomial. Okay? So this is the total Z component. Okay. What other operators can I define? I can define the total X component in exactly the same way. And I can define the total Y component. Right? This is the total Y component. And then I can define the total angular momentum operator acting on the composite system, right? Which would be the sum of these operators. Okay. Now, what you will find very often in textbooks, okay, this is very important to keep in mind, is that in textbooks, you will just find this expression without all this tensor product business. Okay. But you have to remember whenever you see such an expression, and when they're talking about composite systems, that what this refers to is actually something like this. If you don't keep that in your mind, you will get lost at some point. So this is the total angular momentum operator. And similarly, we can also define the total angular momentum squared, which is J dot J. Okay. So now I have my composite system. And remember, so for my composite system, what are my operators? My operators are Jx, Jy, Jz, the total J, and J square. Okay, and this is for the composite system. Now what I want to do, once I have a system and a set of operators, what's the next step? How do I find the states? I need to figure out a way to label my states, right? So how do I figure out the label? Anybody? Pooja? Bhatendra? Karthik? My states have to have labels. Those labels are going to be simultaneous eigenvalues, right? Simultaneous eigenvalues means that I need a complete set of commuting operators. And it turns out, okay, and this is very important, that when you look at these composite operators, right? Jx, Jy, and Jz, and full J and J square. These operators okay, so this is very, very important to keep in mind. Now, the thing is that if you were talking about linear momentum, this would not really be an issue because the linear momentum operators, right? They don't have any non-trivial commutation relation. Px, Py, and Pz, they all commute with each other, right? So we don't have to worry about like if I look at this total momentum operator, and if I look at the x component of this momentum operator or the y component of the z component, right? I don't have to worry about what are the commutation relations between those. But for the angular momentum, I do need to worry, right? Because so I'm calling these the total the angular momentum operators for the composite system, right? But these operators will have the interpretation of angular momentum only if they obey the same commutation relation as the individual angular momentum operator. You understand? So I can always write down these operators, right? I can always do that. But whether or not they actually are, can I call this object the total angular momentum? Like it might be the total something, but is it the total angular momentum? Right? So if it's the total angular momentum, then these operators have to satisfy the commutation relations of angular momentum. All right. And this is a very important exercise. So I want you all to please do this before our next class. And so now, once you have this complete set of commuting operators, you can write down the eigenstates for the composite system. Remember. The eigenstates for the composite system, what are those? What are the eigenvalues? You will get one j. What is j? J is the total, is the eigenvalue of j square. You will get one m. What is m? M is the eigenvalue of jz. But now remember, you have the individual particles also, right? So these are the total angular momentum. So in this set, we have to include, this set is not complete yet. We have to include j1 square and j2 square. So if you don't include these operators, so now with these operators, so it is these four operators, the total j square, the total jz, j1 square and j2 square. These form the complete set of commuting operators. So there are two things to verify. The first thing to verify is that this set of operators forms the angular momentum, satisfies the angular momentum algebra. The second thing to verify is that jz, j square, j1 square and j2 square, all of these commute with each other. Right? See, when I was talking about single particles, for each particle, I had two quantum numbers, right? J1 M1 and J2 M2. Now for my composite system, I have a different description in terms of the total angular momentum, J, and the corresponding magnetic quantum number. Right? But I started off with a system which is described by 4 quantum numbers. So I should end up with a system which also is described by 4 quantum numbers, right? So 2 of those are missing. What can those 2 be? Those 2 will be the eigenstates of J1 square and J2, which would be J1 and J2. So my total state my composite state can be written as J comma M comma J1 comma J. Okay, and at this point, I think I've probably lost many of you because this is something new. So you have to, it takes a little bit of time that you use. Okay. So I'll stop here for today and take your questions. Questions?
So why do we have to include J1 square and J2 square separately in the commuting set?
Because you
Like,
want a,
won't it be included in the main J square?
No, because the main J square, so this is very important to note, the main J square is, so if you write down the, let me, let's look at what we mean by J1 square. So when I write J1 square, okay, what I actually mean is J1 square tensor product I2, right? Because you have to remember that we are working with a composite Hilbert space. Similarly, J2 squared is J2 squared, the single particle J2 squared, sorry, okay, I1 tensor J2 squared, okay? What is this J square? J square is composite Jx squared, composite Jy squared, composite Jz squared, right? Now, and what is J1 squared? J1 square is Jx squared, Jy squared plus Jz squared, tensor I2, right? And what is this guy? This guy is I1 tensor so I'm running out of indices, so I'll write J1x and J1y here. J2x squared, J2y squared, plus J2z squared. And what is the total J square? The total J square is, this is the composite Jx square, right? What is the composite Jx square? It is composite of Jx. Sorry. What is J? Okay, so let me be. Jx is J1x tensor I2, I1 tensor J2x, right? So what is Jx squared, the composite one? It is the square of this whole thing, right?
Yes, sir.
Yes. So now if you look at these expressions and you ask yourself that if I add J1 square with J2 square, right, the composite J1 square with the composite J2 square, is it equal to the composite J square?
No.
It won't be, right? I mean, you might, well, even in general, it will not be, but you might expect that in some special cases, it might be the case. But the form doesn't look anything at all which is similar. So if I look at the square of this, I get J1x I2 squared squared, right? And then I get see now this material is not difficult, but one needs a little bit of energy and patience to do it. Okay. If you are impatient and your mind is running somewhere else, then it will appear to be difficult. But if you remind yourself that there is enough time in life to do this and also all the things you love, like playing video games, for instance, which I also do. So this is the composite Jx square, right? Now, this composite Jx squared is not the same as, this is not the same as J1x squared I2 plus I1 J2x squared, right? It's not the same because you get these cross terms. And also because, well, these expressions, right? So this will turn out to be the same as this. This will turn out to be the same as this. But you have this extra cross, right? So if I write the composite Jx squared, what is the composite Jx squared? It's the composite J1x plus the composite J2x squared. Right? And what is this? This is the composite J1x squared. You understand that before taking the square, I'm taking the composition of the two systems. And here I'm taking the square and then I'm taking the composition of the two systems. Okay. And these two are not the same. So that is why this J1 square and J2 square are not contained within this J. They have their own independent eigenvalues. All right. And
Yes, sir. Good.
okay, I mean, look, you'll have to sit down and work through something on your own before it fits. But I hope that today's class also illustrates to you why I waited so long to introduce the addition of angular momentum. Because this is, it is one of the most beautiful aspects of quantum mechanics, but it is also one of the hardest aspects. In fact, I want to confess to you all that I was a physics major throughout, right? You all are not physics majors. But as a physics major, it was my duty to learn this in my undergraduate class. But I did not understand the theory of addition of angular momentum till I was well outside, well past my undergraduate. So, and this is very important for quantum mechanics, okay? And also for quantum computation. Don't forget. All right. Okay, so I will see you all on Wednesday. Okay. And please remember to go back and revise your notes from last semester. And also please don't hesitate to ask me any questions that you have in Telegram or any other way. Okay. And most importantly, do these exercises. These one exercise, two exercise, these two exercises that I've asked.